Determine if each series converges or diverges. First, we have 1 plus 1/8 plus 1/27 plus 1/64, and so on. Let's first make 1 a fraction with the denominator of 1, and now let's focus on the denominators. The denominators are 1, 8, 27, 64, 125, and so on. These values should remind us of perfect cubes. Notice 1 cubed equals 1, 2 cubed equals 8, 3 cubed equals 27, 4 cubed equals 64, 5 cubed equals 125, and so on. Which indicates we can write the infinite series as the sum from n equals 1 to infinity of 1 divided by n cubed. Having the infinite series in this form should remind us of the p-series test, where for the p-series test, the sum from n equals 1 to infinity of 1 divided by n to the power of p is convergent if p is greater than 1 and divergent if p is less than or equal to 1. Notice here we have p equals 3. This indicates the series converges by the p-series test with p equals 3, which is greater than 1. Let's look at the second example. We have 1 plus 1 divided by the cube root of 4 plus 1 divided by the cube root of 9 plus 1 divided by the cube root of 16, and so on. Let's first write 1 as a fraction, and to fit the pattern, let's write 1 as 1 divided by the cube root of 1. And now focusing on the radicands, we have 1, 4, 9, 16, 25, and so on, which should remind us of perfect squares. We can write the infinite series as the sum from n equals 1 to infinity of 1 divided by the cube root of n squared, which we can also express as the sum from n equals 1 to infinity of 1 divided by n to the power of 2/3. Recall, when converting from radical form to rational exponent form, a to the power of m divided by n equals the nth root of a to the power of m. So once again, by the p-series test, notice now we have p equals 2/3, which is less than or equal to 1, and therefore the series diverges by the p-series test. I hope you found this helpful.